Okay, AP Chemistry Notes, pages 90, 91. We're going to go a little bit into starting to really go into physics at this point. So for those that haven't had physics, which is most of you, it'll take a couple days for you to consume these new terms and such. Even though you might have heard of them, you've probably not used them before. So I have them up here at the top. When talking about electricity, here are three important terms. There are more, of course: voltage, current, and charge. You can think of voltage as the pump that's pumping the electricity, current as the speed of the electricity, like current in a river, and charge is the amount of electricity. Now, if we look at the symbols, voltage is V. Okay, that's easy. And the unit is volts, or just a V. So that one's nice and easy. But now the symbol for current is an I, and just think intensity of current. The unit is called the amp, or ampere, or just A. And for charge, the symbol is a Q, so you can think quantity of charge. The unit's called the coulomb, which you've heard of before with Coulomb's law, and you can just use a C. So you have to be careful that if you see the unit C, it's not current, it's coulombs, which is charge. And likewise, if you see the unit A, that is the unit for current. So like I said, it'll take a few days to get used to this. Now we are still doing electrolytic cells or electrolysis. So we are putting energy in. So the battery's not running forwards, we're pushing it backwards. Or what we're going to look at today, it's not so much a battery, it's creation of a metal solid from its dissolved ions. You might call this electroplating if you want. So like here I have Coulomb is a quantity of charge. It's based on how many electrons extra something has or how many electrons less something has relative to the protons. And here I have the actual equation for current right here. Current is the I, Q is the charge, T is the time, so it's just the amount of charge that passes through a point in a certain amount of time. Now, it's based on seconds, so if you're ever giving some unit that's not seconds, so minutes, hours, whatever, make sure you convert it to seconds when using this equation. Now, I mentioned over here, one electron has this much charge, 1.6 times 10 to the negative 19 coulombs, which is pretty much insignificant. So we don't want to count individual electrons, just like we don't want to count individual atoms or individual molecules. So we will count them in moles. If you multiply this much charge by Avogadro's number, you get this number, 96,485. In other words, there are 96,485 coulombs of charge in every 1 mole of electrons. So we have a new conversion in Moletown, and our new conversion is right here. A mole of electrons is 96,000. Now we'll normally use it this way as this conversion, but just so you know, it's called the Faraday constant, named after an important physicist, Michael Faraday. Faraday is that many coulombs of charge per mole. So it's the same thing. So saying a Faraday is the same thing as saying this conversion. And we'll typically just use the conversion and not even refer to what it's called. Take this first example here. Chromium metal can be plated from an acidic solution of chromium 6 oxide. Okay, A, how many grams of chromium metal can be plated if we pump in this much charge? So that's the amount of charge, or you can think of it as that's the amount of electricity that we're putting in. Well, let's see what's happening here. If we're making chromium metal, that means we're making chromium metal solid, which will be neutral, because the metals typically exist as metals when they're neutral, charged, and they exist as dissolved ions when they're in their ion state or when they're bonded to ions of opposite charge, like in an ionic compound. So it says a solution of chromium-6. All right, solution means it's, just assume it's in water, so it's going to be a +6 charge. So here's my chromium-6 here. And to go from +6 to neutral, you have to gain 6 electrons. And that's going to be important because we're going to need this ratio of how many electrons do we need for every chromium atom that is produced. So I'm going to start with what I'm given, my coulombs of charge, do the conversion from individual coulombs to moles, which is done here. Then, based on my half equation, every 6 moles gives me 1 mole of chromium. Every 6 moles of electrons gives me 1 mole of chromium solid. And then molar mass, moles of chromium, molar mass here, and we get 0.898 grams of chromium, which wouldn't be very much. It's not even a gram. But you should get the idea here. Really, the only thing new that we have done in this problem is just this conversion here. So take a moment and get used to that. All right, let's say we want a whole gram of chromium. How long, so time, will it take to plate out, that's a fancy way of saying create the metal, 1 gram of chromium using a current of 6 amps. Okay, so start with your gram of chromium, grams to moles, same half equation. So for every 1 mole of chromium, it takes 6 electrons. And for every mole of electrons, it takes 96,485 coulombs of charge. So that gives me how much charge I need. And notice on this one, the amount of charge is a little more than what we had above. Up here, it was 1 times 10 to the 4, which would be 1, 2, 3, 4. It's that many coulombs. And notice now I have a little bit more because we're trying to make a little more chromium than we were able to make in the prior example. Now that I know the coulombs of charge here, you can use the equation for current, plug in the current, plug in the coulombs of charge, solve for T, and you get that many seconds. Okay. One big problem left. We'll do it in pieces. This time we're going to make chromium again, but it's going to be coming from a different ion. So chromium metal, again, that means chromium neutral solid. We've got a current 4.50 amp to the cell for 30 minutes. So that's a time, but be careful. You don't want to leave it in minutes. We're going to have to convert it to seconds. Starting with 250 milliliters of 1 molarity chromium nitrate. So notice this time the chromium we are starting with is not going to be a +6. It's going to be a +3 that we're starting with. So first, let's write the equations for what's happening at the anode and the cathode. And to remind you, anode is always oxidation, cathode is always reduction. And then we'll add it together just for practice to see what's happening here. So step A, my chromium's +3, it's going to chromium neutral. That's going to take 3 electrons. The nitrate, well, first of all, the chromium is being reduced. So that's happening at the cathode. If the chromium is being reduced, somebody else has to be oxidized. And your first thought would be, well, it's the nitrate. But nitrate's one of those special ones from the last lesson. Nitrate cannot be oxidized in water. Instead, water is going to get oxidized. So water oxidized for nitrate. One of the three, nitrate, sulfate, and F minus. So here's the equation. Water loses 2 electrons, and it makes some oxygen gas and some hydrogen ions. That will be at the anode, and that's oxidation. So that goes back to the last lesson. So we've done everything but write the overall equation. To do that, you just have to balance it. So since I have 3 electrons here, 2 electrons here, I have to multiply the top one by 2 and the bottom one by 3. That gives me these 2 equations, and just add them together and you see the overall reaction. It's consuming chromium ions and water. It's making chromium metal, which is our goal. So you could an example would be this would be you could coat something in chromium to help keep it from rusting. And we, by accident, make some oxygen gas, which is not a problem, but we also make a bunch of acid by accident. We're going to talk about that at the end. All right, question B. What's the concentration of the chromium ion after we do this process? Well, we know the chromium ion being here is going to go down in concentration. And we need to find how much that is still left, assuming there's any left. So for B, yeah, right there. Take the time, convert to seconds. Sometimes you'll be given time in hours and you'll have to do 2 conversions or whatever works for you. Now that I know seconds, it's hard to read right there, but this right here is the same thing. Those are the same number. 1800 seconds. They told us the current is 4.50 amps. We can solve for Q, the quantity of charge, and we get 8100 coulombs. We can take that 8100 coulombs, convert it from coulombs to a mole of electrons, and then this 3 moles of electrons to 1 mole of chromium ion, that I got that from way up here. I saw 3 electrons for every 1 chromium that is made. Likewise, 3 electrons for every chromium ion that's consumed, and that's the one we actually care about. This one over here really is not. That's what we're making, but it's not in the calculation. So that's where the 3 and the 1 came from. If you wanted, I suppose, you could do 2 and 6. If I do it up here, it'll be better. 2 and 6. You could do it that way if you wanted. But 3 and 1's easier. And that gives me my moles of chromium that was consumed. It also gives me the moles of chromium metal that was made, but that's not being asked for. So let's just see how many moles we started with. Volume times molarity is moles of chromium. That was what we had at the beginning. Subtract what was consumed right here. And this is the moles that remains. Divide by the volume, 0.250 liters, and you get, it is now 0.888 molarity. And it indeed went down. It went from 1 molarity, to 0.888. So we still have most of our chromium ions. It is possible that if you ran it long enough, you would completely run out. Now, someone savvy might say, hey, hold on a second. You assumed that the volume didn't change. The beginning of the problem said 250 milliliters, and I kept the 250 milliliters. And somebody savvy will go, oh, look here, water's being consumed. And they're right. It's usually a small enough amount that you don't have to worry about. So if you actually factored in and took the time to calculate how much water is consumed and adjust that, your volume, instead of getting 0.888 molarity, you would get 0.891 molarity chromium. And it's higher, not because you have more chromium, your moles of chromium is the same, it's because you have less water, because we lost a little bit. For us, we don't really need to worry about that difference, but it's interesting to notice that it happens. And the third question is here. What's the pH of the solution? And the reason this is being asked is because of this accidental hydrogen that's being made. Hydrogen ion, not hydrogen gas. So you can start with a variety of things, but I'll just start with the moles of chromium that reacted, because that's something I know. And if I go to the balanced equation, you'll see that for every 2 moles of chromium, it makes 6 moles of H plus. Let me phrase that better. For every 2 moles of chromium consumed, chromium plus 3, it makes 6 moles of H plus. Let's show it up here. No, it's a mess up here. Let's clean this up. For every 2 chromiums, I really should be more clear. For every 2 chromium plus 3 ions consumed, it makes 6 H plus ions. That gives me my moles of H plus. Divide by the current volume. Again, I'm not worrying about the water that was lost, but if you did, you would get an even higher molarity of hydrogen like we saw earlier, and you end up getting 0.336 molarity H plus. Take the negative log and you get a pH, very acidic, 0.4737. And as I mentioned here, this is why companies that do this, companies that make metals by taking the metal ions in solution and reducing them to the normal metal, like in this case chromium, or you could do it with copper or just about any metal, they typically end up with very acidic sewage. And years ago, this was a big problem because companies weren't regulated. They did what was cheapest, and they would just dump their wastewater out into the environment and really mess things up. Now things are being monitored more carefully, so companies have to be very careful about this. One thing that a company should consider is if you are accidentally making all this H plus while you're trying to make metals or trying to plate things with metals, hey, make something out of this. So maybe the company should go in the business of producing acids as well. So you can produce some acids and sell those in addition to your primary product. And that takes care of this lesson. I'll talk about the homework in class.